Let's talk about qualitative features of polar graphs. Here I've graphed r equals 8 sine 3 theta. It turns out to be a 3-leafed rows, and we want to be able to explain why that's true. We're not going to do necessarily a lot with this, but we want to be able to understand the basics of the qualitative features. The big thing, I think the primary thing to look at is the symmetry. I think that's what appears first, the fact that it has 3 identical lobes, and that also each lobe is symmetrical around its midline, or basically equivalently, the whole thing is symmetrical about the y-axis. Why is that? Well, quickly, I'll go through this quickly. To look at the y-axis symmetry, y-axis symmetric. Well, the way you test that is you take a point, let's say take this point, like C here, given a certain angle, like here the angle is 0.28, a certain theta, I'm getting a certain radius, like about 6. I want to say that if I take the angle over here that's flipped across the y-axis, that I get the same distance. So I have to remember how to flip an angle. So here's how I'd like to say it. We have the old r value is 8 sine 3 theta. We have an original theta, some mystery theta like this one over here, and it has a certain r value attached to it. Okay. Now what I'm going to do is I'm going to create a new r value. That's not working. Okay. That's going to be 8 sine of 3 times. Now how do I get the theta? I take a theta to flip it across the y-axis. We know that that's pi minus theta. That's something we've done before. It's good to review. Okay. So my claim is the new r and the old r are the same number. That when I go out in this direction out here, and I go out in this direction out here, I should get the same r. Well, can I say that? Well, let's see. We do some algebra. 8 sine of, I'm going to distribute that in, and that's a pi, sorry. 3 pi, well, you know what? That's really the same as if we're just pi, because adding 2 pi never does anything to a trig function. So I can change that to a pi. And what do I know about sine? I know that when I take sine of pi minus something, it's the same as the sine of something. No matter how complicated this is, that identity still holds. And I just get 3 theta. That's the same as the old r. And that says that when I've changed theta to pi minus theta, the r did not change, the new r is the old r, and I've got a symmetry. Okay. What about the rotational symmetry? Same deal. Okay. What I'm going to do is I'm going to have the old r. That's the formula applied to some random theta. Okay. So maybe that's going to be like maybe this point here. And then I want to add a third of a way around the circle. I want to go a third of the way around the circle down to here and see if I get the same r value, which it certainly seems like it does. Okay. So I just have to figure out algebraically what does that mean? To go a third of the way around the circle, I'm going to plug in, instead of theta, I'm going to plug in theta plus 2 pi over 3. And then I can distribute the 3 again. Oh, I need parentheses. And the thing is, that becomes a plus 2 pi. I keep writing theta instead of pi. And that doesn't do anything. And that's the old r. And so, indeed, if I go an extra third of the way around, 2 pi over 3 around, 120 degrees if you want to use degrees, I get the same r value. So whatever features I get here, they're going to be replicated here. And all these guys replicated here and here. And you're going to get 3 features. Okay. One note, some polar graphs, many polar graphs, have more rotational symmetry than would come from this technique because of, it's a subtle thing, it's because of the negative r trick. Okay. That can actually add in twice as much rotational symmetry as you might expect. So like, it turns out cosine 2 theta has 4-fold rotational symmetry. It's because of the negative r trick. I just don't want to go into the details of that. Okay. So that's a couple of symmetries. You can look in the book for a discussion about x-axis symmetry and polar symmetry, like symmetry through the pole, going from here across to here. which is really 180-degree rotation, but it shows up in different ways. So here's some stuff, some other interesting features. How big is one of these lobes? That's an interesting question. Let's take this C around. In particular, there's a couple of nice features we'd like to explain. If I'm thinking of this as like a bug traveling on a plate or something, this is his home base right here at the origin. This is as far as that bug ever gets away. That's the end of that. That's definitely a point you'd like to plot to get a good plot of this thing. And it's natural enough. If you plot it by hand, you typically end up plotting it. But it'd be nice to know that it's there and that it's special. Well, that's just exactly how far, at most, can the bug get from home base. Or in other words, what is the maximum R value, and when, in other words, with what theta does it happen? In what direction do I have to point this line out to get that maximum R? One metaphor I often use for polar graphing is you've got a radar beam, and you're sort of sweeping the radar beam around. And sometimes the radar beam bounces off something really close, and as it sweeps around, sometimes it sees something very far away. And then as it sweeps around more, maybe it sees closer objects. And you think of this radar beam sweeping around and discovering these different R values as you go. This is where the radar beam detects the farthest feature that it ever does. Okay, well, let's see. When is that going to happen? When is 8 sine 3 theta at its maximum? Okay, well, let's see. How do I get a sine to be a maximum? Okay, it's going to be when the thing that's inside the sine is pi over 2. Because it's not theta that's going into sine 3 theta, it's 3 theta. But if I can engineer it so that that's pi over 2, I'm going to get it at its peak. And of course, that's going to lead to theta equals pi over 6. So that would predict that this point is pi over 6, and indeed, it's 0.52 radians. I'm measuring this angle here, and indeed, that's pi over 6. Okay, so that's something that's nice to know. You can predict when these outer points of the lobes are going to be if you can figure out when is this function, this r, whatever this function is, if you can figure out the thetas so they get big or small values. And when these are sines or cosines, it's not that hard to figure that out. Okay. Now, what about, here's the most subtle thing I think about polar graphing. There's something very special. If I look at how big the lobe is, what that really is determined by is what is this magic angle as the radar beam detects something coming right towards home base, and then it flashes all the way through. It's kind of funky with the negative R trick. But as these R's get smaller and smaller, what is this magic theta? Well, it looks like it's getting very close to pi over 3. Looks like this lobe is exactly 60 degrees, subtends a 60-degree angle. Well, how could we figure that out? Well, let's see what the radar is telling us. It says we want to look for a magic angle where the R's get closer and closer to 0, and in fact, boom, right when it becomes 0, you can't really put it on there with the picture, that's when this line is going to be going in the direction, basically tangent to this curve that's coming in. Okay, so what that says is that if I find a theta which gives r equals 0, that gives a direction in which the curve comes into or goes out of, just depending on your perspective, the origin. Because that's r equals 0 is the origin, and those thetas are going to be this kind of line. Okay, that's a pretty funky thing. Okay, so we can do that. That's easy to do. We just set 8 sine 3 theta equals 0. Well, we know how to solve that. We know that sine 3 theta equals 0, or in other words, 3 theta equals pi, or 2 pi, or for that matter, 0. It's really k pi. And so 3 theta, or theta rather, is 0, or pi over 3, or 2 pi over 3, or 3 pi over 3, but let's see. Actually, no, let's keep going. Or 4 pi over 3, or 5 pi over 3. Now it starts to repeat. 6 pi over 3 is really just 2 pi. That's really just 0 again. So there should be 6 places And indeed, that's right. It's the start and end of every one of the leaves. Theta is 0. Theta is pi over 3. Check it out. Yep. Then theta is, well, now this is getting, okay, here we are. Theta is 2 pi over 3. This is pi, which is 3 pi over 3. This is 4 pi over 3. That's 5 pi over 3. And then back to 2 pi, which is 0. And so this simple calculation, setting r equals 0, or in other words, the formula for r, 8 sine 3 theta equals 0, gives you this very important information about how it slices through the origin. So that's a nice thing to be able to do as well.